Hey, I'm John Keiser. I work at Chef. I'm a lead of Team Ronin, the wandering masterless samurai of Chef. And I'm a resident mad scientist. Not the only one. The company is kind of populated with mad scientists. It's a little scary around Christmas. So I came to Chef as a developer who was working on distributed systems, and I was very frustrated because it was really hard for me to configure systems. I didn't like it. I don't remember the things that I need to do, and there's a lot of stuff that I don't know about it. I came to Chef because I hate configuring systems so much that I needed to work at a system configuration company and fix the problem and never have to do it again. So configuration management, it turns out when I got here that it's not just my problem. It just turns out the configuration is hard. And many of you probably remember the days before Chef where you had to remember a whole series of commands anytime you wanted to configure one of your hundreds of machines. You had to get into the machine and manually install things. You had to edit the text files in a particular way. If you wanted to change your keys, you had to remember which commands and where the keys were. And so the terrible ops people would remember it, get hit by a bus, and then their company would fail. People who were pretty good at it would write it down in a notebook. People who were very good would put it on a wiki somewhere, and it was called the playbook. But none of these were really very helpful because playbooks are really long, and it was hard to even find the commands that you needed. Well, this is where Chef made its entrance. You all know Chef. I'm not going to spend much time talking about it, but finally we had some kind of a tool where we could configure things idempotently. We didn't have to worry about update versus create. We could write down our configuration once and remember it in code, and it was real. It wasn't out of date with what was actually supposed to be there. It was really nice. And we have this problem in Chef where we still have playbooks for some things. We are not using Chef for everything we should, and so there's kind of a running joke whenever someone complains about an INI file that they have to put up there. Oh, you just needed to add that file. You forgot to put the key over there. Well, if only we had a tool that could have done that for us. Yeah, and I don't really need to explain any of this to you. We have that joke pretty often, but we still have a playbook. And it's a little bit hard to see on here, but what you're seeing here is one snippet of the ops code configuration for hosted, the wiki that tells you how to create the servers that run hosted Chef. You can see there a rabbit box and a solar box that is handling all of your searches. Knife EC2 server create commands. I can't remember what the AMIs were supposed to be. I don't know. I didn't even know what the flavors were, and I didn't know what the commands were supposed to be. So the playbook was how I would figure out how to recreate machines, how I would figure out what machines were even in my cluster. And it's one day I was making the joke, if only we had a tool for, wait a minute, let me come back in a couple months and finish that joke. It turns out we didn't have a tool for that yet. The clusters of our dreams are really are fuzzy and happy, and they're many tentacled. They have many machines, but we can make lots of them. We know what they're like. They are our friends. Clusters in reality. This is The Call of Cthulhu, an animated children's book, by the way, and that's Dr. Seuss verse explaining the entire Call of Cthulhu. The real clusters are mysterious things that we've summoned from the depths, and we know not whence they have come. You know what? It's how do I version my cluster? How do I know what it is? How do I test a cluster? Like, can I stand up another one? How do I recreate it? How do I manage the machines in it? I don't even know which machines to manage. How do I add capacity? My information is always out of date. My memory sucks. Nice EC2 create takes 10,000 args. Some of my machines have SSH, some of them have WinRM. I just want to converge. This makes Buddha sad. So, turns out, if only we had a tool for that. This is Chef Metal. In fact, this is the entire heart of what Chef Metal is. Chef Metal is a tool that gives you the machine resource. You can see here a Chef Metal recipe explaining two machines, a database and a web machine, and the recipes that are going to run on them. This recipe is meant to be a description of my cluster. It's a fairly simple cluster. One that I can stand up, one I can check into source control. I can upload it to my Chef server. I can make two of them. I can make a test version of it. I can do a lot of things with it. But you'll notice one thing that's missing from this is, like, where does it go, right? This just tells me I've got a database and a web machine. Not very useful if I don't actually have machines, huh? So there's another counterpart in Chef Metal, which is the provisioner. You have the machine resource, and every machine is housed somewhere. In this case, it's Vagrant. This is how you declare a Vagrant provisioner in Chef Metal. You put this directive somewhere before you declare your machine. And what it says is that there's a directory, and that's the kind of the playground where all of my Vagrant VM files are going to be. And that box thing is essentially options for the provisioner, saying, here's where the Ubuntu 14 Vagrant box is, and that's enough information for Vagrant to stand up a VirtualBox VM with Ubuntu on it. When I take just these two recipes together, this is what it looks like. Demoing will add some time, and I want to have a bunch of time to answer questions at the end. So this is, just trust me for the moment that this is how it looks. I have redacted parts that are useless, but you can see it creating the machine named DB. It's running Vagrant up. It is writing a client RB file onto the machine, and it's installing Chef, and then it converges Chef. So that's what the machine resource does. It goes to Vagrant, defines and creates a machine, or in this case, Vagrant, goes to its provisioner, defines and creates a machine, and then it runs Chef client on that machine, installs it if it needs it. And you can see the same thing happening on machine web 1. You see that place right there where I install Apache. Just don't look too close at it. And at the end, you can see two resources updated. That's pretty cool. You can see a little picture. This is your workstation. It's got what's actually happening there is Metal is running on your workstation, and it's creating those two machines in Vagrant. And the nodes and clients, the core Chef objects that correspond to your machines, live in a Chef 0 instance on your machine. And that's just because what we ran was Chef client-z, local mode. We could run this against a Chef server, and it would store those objects in the Chef server. What it means to have those nodes in the Chef server is that you can search them, they can find each other. So this is what Chef Metal is. It's a machine resource and provisioners. It turns out just having that one resource enables a whole world where we can define the topology of our cluster. It gives us a place where we can define all the other things associated with our cluster, the private keys and the encrypted data bags, the things that are kind of global to a whole cluster. The kind of provisioners that are supported, we can hook up a machine to a cloud container like a EC2 or Google Cloud Compute, VMs like VirtualBox and VMware, containers, LXC and Docker are supported right now, and bare metal, from whence the project gets its name, where hook it up to Razor and things. We don't have those provisioners yet, ironically, but don't ask me why it's called Metal. So the nice thing is a Chef, you run Chef client. When you make these machine resources, you're putting them into a recipe. And that's what makes it powerful. you're not just declaring the machines in your topology, you can declare all of the other things around it that support it. And that means that if you need a particular data bag, if you need a load balancer in AWS, you declare it in this recipe, and then if you want to stand it up again in another AWS account, you run your recipe again. It's unified, and what I mean by this is Chef Metal stores information about where it created the node, enough information to get back to it inside the node, so that you can run commands like, you can run a command on the node, you can delete the node, you can converge the node without having to remember all the parameters that you specified in the first place. You just tell it the node name, it can look up the provisioner, and it can connect and do the things that it needs to do. Doesn't matter where it is, whether it's Vagrant or AWS or in a container. Another nice thing about being in a recipe is that it's idempotent. Adding a new machine to your cluster is adding the machine directive to your recipe. If you run the recipe that I just created, where you add web2 at the end of the recipe, then it looks a lot like this. You see that DB and web1 were already there. It noticed that Vagrant already had them. And web2 wasn't there, so it created it, ran Chef Client on it, and installed Apache. Don't look too closely at that. And we have the same situation here, where from your workstation you run Metal. It only created that one machine. It hooked it up to the same Chef 0 instance, and all is good. So we want to be able to use these recipes again and again. So we want to melt it down and run it again. So let's say, what if we wanted to point that recipe at EC2 instead of Vagrant? Well, if we'd split those, the way we wrote those in the first place was on two different slides, two different recipes. One was named vagrant.rb, and then one was named cluster.rb. What we're going to do is we're going to make an EC2.rb that just has this in it. This is an EC2 provisioner. It turns out that AWS already has a default location for your credentials, so it'll look them up there. And it's got a default AMI that you use. You can specify different credentials and different AMIs and load balancers and all the crazy stuff, but this is all you need to basically get started. So we're going to stick this in an EC2.rb, and we're going to run Chef Client, and it's going to do this. It's full screen. No, you can see it's AWS. So it's going to create web1 and DB on AWS, and they're going to be linked back to your Chef 0 instance. And if you think that's kind of interesting that an EC2 instance is storing data locally, it is, but it does actually work, and we can talk about that later if you want to ask questions about it. Now that we've got our recipes up and we've got them, we can create test clusters, we can put them in production. It'd be nice to get a little continuous integration. The way that you would do that is you would take the same Metal recipes that we've created already and check them into your GitHub repo along with the rest of your source. When GitHub gets updated, the Jenkins node will pull it down, run Chef Client with the Metal recipe, stand up your cluster, and then run whatever tests you want, hit the web server, whatever you like, then tear them down, and then repeat and rinse and repeat each time. Oh yeah, I was going to move that first. You should still stare at the glory of the hamster mech. And so this is what it looks like. There's a Jenkins machine, whether it's in AWS or not, and it runs Metal, stands up the stuff inside AWS, and brings them back down. Same recipes we created, not very much text here. When you move things to production, there's a concept of a provisioner node that you saw yesterday in Mandy's talk. The provisioner node is a node that's sitting in production that is provisioning the rest of production. Because you don't necessarily want to be at the whim of whatever workstation people have set up at the time. You want to have a nice consistent environment for provisioning, and you want to know exactly where the provisioning is coming from, how it's controlled, So what happens is you upload this cookbook to the same chef server all the rest of the cookbooks are. This provisioning node has that cookbook in its run list. And when you want to change your cluster, you just upload it to the chef server and wait for that provisioning node to run chef client again. It'll pick up the cookbook, run metal, and if you just added a web 2, it'll go and create a web 2. That's way off the screen. That's a chef server up there. And that's your real chef server because your workstation is no longer involved here. Provisioner node runs in EC2 or Google Cloud Compute, wherever you are. And it's going to create those two machines and hook them up to the chef server. The provisioner itself is also hooked up to the chef server. And growing the cluster is the same thing. We add a web 2, and the provisioner adds it in EC2. The fact that we're in recipes means that we are doing code. And the fact that we're doing code means we can do some really interesting things that we can't do with a static configuration model. We can make it dance, just like Billy Joel. This is Uptown Girl. I figured upscale, Uptown hat. So the fact that you're in code means that you can actually, you can write a loop. And it's easy to write a loop that goes up to a constant, say 1 up to 3, and let's make 3 web servers. But you may as well stick that constant in a variable, and you may as well drive that variable by your monitoring software. Like say you check the CPU percentage usage on all of your current web servers, and they're really full, or their unicorn queues are backed up, whatever you decide is your criteria, and bump up the number of web servers by 1 or 10% or whatever. When you up that number, it's going to create some more machine resources. The machine resources are going to go up and check and see if the machine exists. And since it doesn't, it's going to create some more machines for you. An obvious corollary when you're thinking about upscaling is what happens when you don't need those machines anymore. Again, you can drive those decisions yourself. I don't want to spend too much time on this, but I did want to have a slide. If you're going to see upscaling, you should see downscaling. What this piece of code is doing a search to find all the web servers, and then just deleting the ones that it doesn't need. It's looking to see if you went down from 12 to 10, then 11 and 12 are going to be greater than the number of web servers, and it's going to drop number 11 and number 12. So those are most of the scenarios in which you can use metal. And I wanted to talk a little bit here about how provisioners are made. It's been actually probably the biggest question I've gotten over the last couple of days. And how is time? I want to make sure we have a lot of time for questions. Okay. Provisioners, it turns out that they are actually pretty easy to make. There are 2 other people that have just kind of stumbled across the Chef Metal repo, started using it, and made provisioners. The ones that we have right now that are released, there's a fog provisioner that already has been tested against EC2, DigitalOcean, and OpenStack. Should support Google Cloud Compute and a ton of other things that the fog library supports. Most cloud solutions have something in there. Vagrant, which supports VirtualBox and VMware. There's a bare metal provisioner, but it's not using Pixie yet. That's one that Zach Zondio wrote, and it will take a list of IP addresses for machines and SSH to them, but they already have to be set up with an OS. Containers. We have an LXC provisioner and a Docker provisioner. Container provisioners are often going to be pretty specific to the container technology being used. There's no fog for containers right now. So they're pretty easy to make, and this is what you have to do. There's a provisioner interface that is in the Chef Metal repository. The interface has pretty good documentation on it. What you do is you extend it, and there are 4 methods that you have to create. These 4 methods are create a machine, get a machine, delete a machine, and stop a machine. Get Delete and stop turn out to be pretty trivial in most things. Stop just means power off the machine. Delete means I don't want it anymore. I don't want to pay for it anymore, please. The only one that is of any real consequences as far as building a provisioner is acquire machine. This method is the one that Metal calls when the very first thing when you have a machine resource. And actually, that should be acquire machine, not acquire node. The basic pseudocode for it, though, is still pretty simple. If the node is already associated with a machine in your cluster, and I'll talk about how that association is made in a little bit, make sure that machine is started. Like if it's powered off or whatever, the provisioner's job is to, the contract is that at the end of the method, a machine will exist and be powered up and accessible so that the rest of Metal can do the setup and chef converge and all the other wonderful things. If the node is not associated with a real machine, go create it, grab it, whatever it is you need to do. In Vagrant, it means creating a VM. And in EC2, it means calling the EC2 API and asking for a new machine. And then return a machine object, which it turns out there's a lot of logic sitting in a machine object. And if you had to make it yourself, it would be a lot of work, probably. But in every case that we've seen so far, the existing machine objects that are sitting in Metal, you can just instantiate one of those and return it. And I'll explain what those are. The machine object has a bunch of methods to help Metal interrogate the machine and do things on it, like executing commands, manipulating files, uploading and downloading them, and converging the machine, setting up Chef client on it and running it, or in some aspirational cases, running a Chef client run locally and just modifying resources on the target machine remotely. So the ones that are already there are Unix machine and Windows machine. Some of the things like test whether a file exists are different in PowerShell versus in Bash. And so the Unix one implements the Bash and Windows implements PowerShell. And that's covered all the use cases that we've cared about so far. The machine object has a couple of helper objects that you pass to it, because a Windows machine could be on the end of an SSH or a WinRM protocol, and we want to be able to support either one. We don't want to force you to run SSHD on every single machine you have. So you can implement a transport, which is a much lighter weight object. It can execute commands, upload and download files. And again, everything we've seen so far has been able to do one of these. When we write a container one, we tend to have to write a new transport because we don't want to rely on the container having network access, because not all containers do. The other object that you associate with a machine, that when you return that machine object, you're going to give it a transport and a convergence strategy. This one is all about installing Chef client wherever it needs to be installed and converging the machine by running Chef client. There's a bunch of different strategies that are already there. You know install.sh probably, which is that script that is hung off of opscode.com. That if you download it, it'll detect what machine and download the right package and install it. And there are some other ones that will do it a different way. And if you want to talk about those, we can talk about them. But picking a convergence strategy is pretty easy to do. Only reason this slide is here is that's just about all the code that you need to implement that one complicated method. And I just wanted to show how long it was. The only bits that are hand-waved here are lookup server and create server, because those are the things that would hook up to your infrastructure. The other methods are connect to machine, delete machine, and stop machine. And they're pretty easy to implement. They're going to vary by provider. Connect to machine is the only one that could use a comment. Connect to machine's job is to give you that machine object so people can call Chef client or execute commands. But it will not try to idempotently start or create the machine. Its contract is just, I know the machine already exists, I want to talk to it. So this is where we talk a little bit about the provisioner options. Every provisioner, every cloud provider, every Pixie root has got a different set of options for how you decide what kind of machine you're going to get, how big it is, where it's going to be, what region it's going to be in. And Metal's philosophy is to stay the hell out of the way. The provisioner options is a free-form hash that you, when you're writing the provisioner, decide what options are in it. The user can pass anything that they want in the hash, and the provisioner can do whatever it wants with those things. You can see in EC2 provisioner options there, you can pass an image ID and a flavor ID, which have nothing, like, they don't mean anything on most other provisioners. And you can see a vagrant one where we pass an actual string with some config. That right there will mount my code directory into a vagrant VM. And I wanted to point out with provisioners and provisioner options, the fact that we separated some recipes, defined a provisioner in one recipe, and then defined machines in a separate one, doesn't mean that all machines have to be in one place. Different machines can be in different data centers, can be in different VMs. Some of them can be containers, and some of them can be in EC2, and all of them can be mixed in the same recipe. You can either say with provisioner, which means all machines declared after that particular with provisioner will use that provisioner, or you can declare the provisioner attribute on an individual machine, which isn't shown here. But that's all with provisioner is doing, is stashing the provisioner in a global, and anytime you declare a machine, it stuffs it in the machine's provisioner attribute. You can do with provisioner options to the same kind of thing, and there is also a provisioner options. You can also vary which chef server they're pointed at. So if you really want to define two environments that are pointing at different chef servers, you can do that. So the philosophy is that you should be able to define your entire infrastructure in one recipe or set of recipes. You're not going to be locked down to a global config. Actually, before I talk about where we're going to go from here, something I promised I would talk about and didn't was how we associate how we tell Metal where the node is. As a provisioner, you'll notice there's a line right in the middle there where it assigns something to provisioner output. There's a free-form hash in a node that the provisioner owns, and the provisioner stashes the ID or whatever other information it needs that identifies that machine on his cloud or his Pixie region. It could be the MAC address, it could be the instance ID for EC2. Something that identifies it can get you back to it. And it stashes it in the node, and that way the next time it comes back around, it will be able to find the node again, reconverge it, try to start it back up, make it idempotent. This is where the idempotency happens. One little bit about this is you can see that it's stashing it as soon as it creates a server. That's even before the OS is laid down, because the part where it's going to wait is going to be in server.start. We want to stash the ID of a server as early as possible before most work is done, because we're paying for these things, and if like the script crashes on the save node or on the next line, then you've created an EC2 server that you're paying for and you don't know where it is anymore. So we try really hard to stash the information about where things are as soon as possible. So where we're going from here, Chef Metal right now is alpha, and there are some things that I think we need to get done before it can be final. The big one is parallelism. We're used to starting a machine in EC2, taking a few minutes, that's okay. But Chef executes resources in serial right now, and it'd be a pain in the ass to make 50 servers at 3 minutes each. You're talking about an hour and a half to just make, that's stupid. So we're going to add parallelism into Chef resources so that it can run all of your machine resources at once if you want, or you can say I want to run one of my resources and then I want to run the other 50, like my database and then my web servers. But make it so that it's going to take you 3 minutes to create those 50 servers and not 150. Remote Chef Converge is a thing that we want to do for containers in particular because I feel incredibly dirty for, right now, in the Docker demo you saw yesterday, I installed the Chef client in there. I'm sorry. Like that's a whole lot of stuff to put inside your container. And in a lot of cases, you just want an executable in a file. So what we're talking about is making a minimal Chef client run that can run on the host, and you can write a recipe just like usual, but you use file and package and execute, and just it will put the files up into the container remotely using the container's transport. You won't have any overhead in the container. And more provisioners, like I've talked to a number of you. There are plenty of provisioners that we don't support yet, and whether they are private or public, I will help you get started making them if you're having any trouble. So yeah, how you can help, right? Provisioners, use it and send feedback. The shape seems to be working so far, but we want to, before we release it, we want to make sure that the shape of this resource is the right one. Because what's going to happen is we're going to merge it into Chef. The fact that we're calling it Chef Metal right now is really just to put a circle around the idea so that we can all talk about it. Eventually, it's going to lose that boundary. It's going to be part of Chef. And file and fix any bugs. So, any questions? Yes?
Wait.
Oh.
So, if this comes into Chef, it replaces all the provisioners, like knife EC2 create and all that sort of stuff? Was that sort of the goal?
Yeah, the goal is that those. So the question is about whether this replaces knife EC2 server create and all of the command lines. Yes, those will use the same code. We want those to use the same provisioners. We want them to be convergent. But I don't think that all command lines go away. There might be a more streamlined command line that does it, but just because recipes might be the best way to define a cluster doesn't mean sometimes you're going to want to make a one-off machine.
Yeah, absolutely.
So anyone who's used Chef a fair bit has done notifies. When something updates in one place, you go do something someplace else. It seems like with machine infrastructure in particular, especially in a test world, I might want to have something done beforehand. Like, I'm going to spin up this, I'm running the thing that spins up my API server, but I needed to go spin up these two other components, as the database and the message queue. Mm-hmm. In brain fade, try again. In the Chef world, we don't really have a way to define those kinds of dependencies back without doing strange, action nothing and then doing overrides and whatnot. If I have a master copy this is my entire infrastructure, but I don't want to run the entire infrastructure in Vagrant, I want to run one piece and its dependencies, how do you see us being able to reach that?
You want to run one piece of the infrastructure in Vagrant.
And start up any of the things that it depends on.
I would, the way that I would probably do that would be to have a recipe that specifies its dependencies that runs before the recipe that specifies the thing you want to put in Vagrant. But I might be missing a piece of your question. Can those machine resources, can the dependencies of this Vagrant machine be spun up using machine resources, or are they?
Yes. Assume that, right?
So one thing that is true about this and will always be true is that you can specify the order in which things are spun up. Like obviously in Chef right now, you already have this. If resource A is declared before resource B is declared before resource C, then they go in order. You also have notifies and subscribes, and those, which means that you can, when one action finishes, one resource updates, it can notify another resource and have it do its thing. And if a machine resource subscribes to a file changing, then you can make it so the machine resource will spin up and create the machine after the file changes. So that's another way of specifying order. And the final thing is, even when we add parallelism, those mechanisms will still be in place.
Okay.
Cool. So I'm wondering about modifying machines. Sorry. I'm wondering about modifying machines. So it seems like a convergence is predicated solely on having an ID of a server. Mm-hmm. If I want to change the size of a server, let's say, I spin it up as an M1 large, and then I realize how I need an extra large. How do you see that working in Metal?
I don't think the idea of, I don't know yet how to generalize the idea of an evacuation from one server and a move into a new one. So probably in those cases, you would end up using the machine X action delete and then a machine X action create. One thing that I'm going back and forth on is whether the machine resource, like say it was an x1.small, all your web servers, and you update 9 of your web servers to be x1.large, and one of them is still a small, but your definition says it should be large. You could have the EC2 machine provisioner toss an error saying, I don't know how to evacuate this machine and move it there, but user, you should at least know this isn't a large machine right now, and you probably should do something about it. There are going to be with any resource, there are going to be some things that can't safely be done automatically, and with them we just notify the human.
Sure. So another question I had, it seems like at least the initial implementation is fairly instance or server focused. Is that true down the road, or will there be additional provisioners, or are there ways to accommodate like different sorts of resources, like load balancers, networks, firewalls, et cetera?
For provisioning network files, or network firewalls and routers and things like that, you mean?
Correct. Like all the pieces to assemble your servers into something bigger.
Yeah, actually, once we started, the answer 3 days ago was no, I don't know how to do that. But during this conference, we've been talking about this idea of a remote converge, where you could write a recipe for something and have it run on your workstation, and through a transport or a protocol, modify the remote machine. And that's what you need for a lot of network firewalls and routers, because they don't go over, like you can't install the Chef client on them. So I think the answer is we now have an idea of how to do it, but I don't know precisely whether or when. It sounds, if we can get close to it, it would be a pretty killer feature.
Would you mind elaborating a little bit around the ability or the roadmap around a policy definition, if you will, that will allow you to define a min and a max number of instances of a type, and maybe like a stepping or a tiering based upon some sort of metric that you'd be able to find, like CPU hit 80%, it's now time for me to add one because the policy says I can add +1, as opposed to the the manual step.
Yeah, so the upscaling and downscaling? Like being able to say, I should have more. I've thought a little bit about this, but I've never done it in production, and so my guess is that the right way are, I have a hunch that the first time anybody does this, they will do it wrong. And I'm sure, and I know that people have done it before and have done it wrong the first time before. So they're going to be better people than me to answer the question. My imaginings have me thinking we want to make sure that we upscale it slowly so that we don't have runaway servers going up a lot, and we do the same with downscaling. But which metrics you use and how fast you scale, I think they're questions that other people will be able to answer a lot better than me. I can provide you the mechanism to do it, but there are a lot of much more experienced people than me that can do it.
I have a question about, it looks like right now you store data about created server on inside of Node, so it's Node specific.
Mm-hmm.
And if you go to production, it's something like you want to be HA available. So for example, if your provisioner goes down, like your provisioner node goes down, right now you lose all the information about what your servers really are.
So in production, what you will almost certainly do is store the nodes on the chef server. Let me see if I can find that slide. That was one thing. Like we started this story from a developer workstation. Yeah, see that chef server up there, off the top of the screen. You would in production you're going to be running a real chef server, and there's two things about Metal that allow it to talk to that. First of all, wherever you run the chef client from, if you don't say anything else in the recipes, it will put any new nodes it creates onto the same chef server that your chef client is running on. So if it's a provisioner node, and your provisioner node is on that chef server, anything it creates by default will go to that same chef server. Chef 0 is not a default, it's just you happen to run it, if you happen to run it in local mode, then nodes go there. But in production, you're going to be running against a chef server. The second thing is, even if you are running locally, you can put a with chef server directive into the recipe and say, any machines that I create, even though I'm running local mode, I want those machines to go up onto a chef server.
Who provisions the provisioner?
Initially, a workstation. And I think that's probably the right way to bootstrap an infrastructure. The more complicated version of that question is what happens when the provisioner node goes down. And I think you have a similar situation to when, like, who watches the watchers when you have monitors. The way that we solve that at Chef is to have a monitor sitting in a different data center that is watching the monitor that's sitting in our main data center, so that we at least know when it goes down and can fix it. I think you would probably do the same thing with provisioners. You could build a highly available one. Like, I know that there are lots of ways for you to make sure there's only one of a thing running, and so you'd have two different provisioners that are both running the cookbooks, but only one of them is ever converging at a time. But there are standard ways to solve this kind of a problem where there's a master, and we need to make sure that if it goes down, we heal.
Currently, when a node is idempotent, or when you're accomplishing idempotency with a recipe, say it's a template or something like that, you're actually checking against the file on the node, running a hash, right? Seeing if the file that's being generated is a new hash or not, right? So are you doing this now against all this data and not against reality? Are you not looking out at the provider and saying, is this machine like it's described in the resource? Or it seems like you're creating a different type of idempotency where you're being idempotent against the data in your chef server instead of against reality.
No, we're checking reality every time. So what the idempotency that happens, like let's just use EC2 for an example. When you come back to the node, you say I have a machine DB in this case. That provisioner, when it runs into that resource and tries to run it, is going to grab the node from the chef server, and that is going to have the instance ID in it for EC2. It'll take that information, go to EC2, and say, hey, do you exist and are you running? And if the answer is yes to both of those, then he'll just return the machine because he's checked against reality. If the answer is yes to both of those, he will then check if SSH is working on the machine, because there is a condition where the machine has started but SSH isn't up yet. And then once he's checked that, he'll return the machine. Same thing with files on the server. Yeah, idempotency should always be against reality and not against your picture of it.
Cool. So I know there's lots more questions, but
The reality is that there's a keynote after this, and they have to take this wall down. So this is a super awesome topic. Thank all of you for coming. John is going to be around, and I know that you all have questions. So do you mind taking the hallway track for a little bit? Okay, John is going to be in the hallway track.